Hello, so today we are going to do this problem, part of Leetcode April Daily Challenge, binary search tree iterator. So what the problem asks is we get a binary search tree root node, and we want an iterator over the in-order traversal. So in-order traversal is left first, and then the node, and then the right side. And we get the constructor gets passed the root node, and the root. They mention here the pointer should be initialized to a non-existent number smaller than any element in the BST. It seems to be a suggestion, but we don't have to follow it. And then here we have two functions that we need to implement: hasNext and next. HasNext returns true if there exists a number in the traversal to the right of the pointer. Basically, HasNext needs to return true if there are still elements to process in the in-order traversal, and next returns the element itself. Then each time it returns the next element in the in-order traversal. So that's kind of what we are asked. So we need an iterator that iterates over the tree in an in-order fashion. Okay, and then we can assume that next will only be called if the traversal still has some nodes. So we don't need to check if there are next elements using maybe hasNext. We don't need to do that since we are guaranteed that there will be a node when next is called. Okay, so that's pretty much it on the description side. If we take a look at this example, first when next gets called here, we return the far left. That's what in-order traversal does. So we return this node 3. That's what we have here. And then after that, next gets called again. So now we are pointing to here. In the in-order traversal, it's left, then the root. And now we return 7. And then as next gets called, we still have elements, right? And so we return true. And then next gets called again. Now this is important. So after the node, we process the right side, but the subtree, this subtree here, what it does is also in-order traversal. So we start with the left side, and then do the node, and then do the root. So that means that this is the first one we need to return. So we return 9. And then hasNext gets called again, we still have elements, and so we return true. And then after the left, so it's always left, node, and then the root. And so after that, the node, right? So 15 gets returned. We still have elements again, so we return true. We called this and we called this. Now next gets called again. Now we did the left side, the node side. We need to return to go to the right, and so we return 20. And now we are done. After 20, the children are all none, and so hasNext should return false. And so that's what we do here. So this is kind of what is asked from us. Now let's see how we can implement it. So in-order traversal is very simple. We can do it recursively, traversing the left, the node, and then the right. The simplest solution would be to just construct a list of the in-order traversal. So in our case here, that would be just 3, 7, 15, 9, 20, right? And we can just have an index which starts out at the first position, and then we keep going. Each time we do next, we increase our index. And so first we return 3, then we return 7, and then the next call to next, we increment I, and then we return 15. And for hasNext, we just check that I is still less than the length of the array, because that means we still have elements to traverse. Okay, and this is the result of the in-order traversal. So this is the simplest solution we can do. It of course uses extra space here, of an extra space, because this is the number of nodes. So there is that downside there, but getting the next element is O of 1, because we just return array at position I. hasNext is also O of 1, right? So but memory-wise, it uses O of n. So in the follow-up here, they ask us to implement it with next and hasNext running in O of 1 time and O of h memory. And so this doesn't satisfy that, but we can implement a second solution that potentially does that. Yeah, so let's jump into this first solution and then we can iterate from there. Okay, so we need to do first our in-order traversal. So we need to define our in-order function. I will define it here. You can define it as a class function here if you want, but I'll just do it here. So to do that, we need to check for our base case and then return an empty list. And then here, go left, add the node, process the node, and then go to the right and return this. So this is very simple in-order traversal. Now what this would mean here is that we need to store the values, right? So self.nodes, or we call them in-order nodes, is going to be just calling in order on the root, right? And now in next, we need to initialize also our index that we mentioned here, right? So index starts out as 0, and so next needs to return in order nodes at position I, and then we need to return node, and then we need to increment I, right? So that's the first step for next. What about has next? For has next, what we said is just we need to make sure that the index is still smaller than the length of our array. We can also just initialize here the length, but otherwise we can also do length of self that in order nodes. Because has next will be called multiple times, I suggest you can do just something like this to make this faster. And that's pretty much it, right? So let's run this. Yeah, this should be self.I. Let's use more examples. Okay, let's submit. Okay, so this passes test cases. Now, how can we do it in a way that doesn't use extra space? We have two ways to do this. One is using doing iterative traversal, iterative in-order traversal. The other option is to keep using the recursion but use a generator. So we'll see those two solutions. I'll start out with the generator solution and then from there switch to the iterative version. Okay, so let's switch to the Iterator version first. So for the Iterator version, we need to do the same thing, but in a way where we use a generator here. So let's first switch to a function here, just to make this easier to see, and I'll call it in-order generator, right? And now since we are no longer using a list, we'll just return when we reach the base case. And let's separate these two here. And now what we need is to just use yield that allows us to, each time we call next from the generator, we get the next element in the right order. So here we'll do yield from, and here we'll do as well yield from. Now here we'll do yield this value. Okay. And now what we can do is, so now that we get the value from that, we no longer have an index and we no longer have an array. So let's get rid of these and this. However, let's keep track of our generator. So it's going to be generator here, and this will need to be self.dat. And since this is a class function now, we need to do self. And now that we have the generator, we need to return it here, right? So how can we do this? So one way we can do this is to keep track of the next element in a variable. So to get the first element from a generator, we just use next. And so here we can just do next from our generator here. And now here we can return that self.current. However, each time we get next, we need to advance where our generator is pointing. The first time here, we want to just put node val, or maybe value here, is equal to self.current, so that we can return it. And here now we are free to change self.current. What should it point to? The same thing we did here. So next dot. Basically, you can think of an iterator like pointing to wherever we were in the right order in the in-order traversal, and each time we just do next and go to the next element. So basically, what this would mean is that since we do this yield from in-order traversal, it will go all the way down to the left side, and so it will be pointing to 3. And next time we do next, it will point to 7. After that, when we do next, we need to point to 9. And so basically in the next function, we prepare for the next iteration. Hopefully that makes sense. And now we return the value. And then here we do next.generator. And then what should we do for has next? Now that's where the problem is. So with the generator, you don't have a way to tell that you are at the end. The only way to do it is to call next on your generator and then have that throw an exception in Python called stop iteration. Only then you will be able to tell that you are done, right? So what this means here is that we need our function here to support when we are done. And so to do that, I'm going to do a small change here. I'm going to return just nodes. And so this would be node. Still the same thing, except the generator returns a node instead of its value. And now, for has next, what I will do is I'll define a function here. Or actually, let's do it here. So what we can do is say, so for next, when we call next, we assign self.current to the next value. We will do has next basically when this is not none. Basically, there is still an element. But this can throw an exception. It can throw an exception when when we reach the end with stop iteration. So to do that, we'll just do try. And then here, we will catch the stop iteration, which means we are at the end. And with that, we will mark that we are at the end by assigning none. And basically, that will cause this to return false. Okay? And that's pretty much it. Yeah, so each time we do next, and then here we have our generator. Yeah, so that's pretty much it. Let's run this. So yeah, so we need to call the same function. So self dot. Okay, so it looks like there is a little bit of a set of problems here. Okay, so these are correct. And then we initialize our generator here. We call next on the generator. And for next, we initialize the node to this. We go to the next iteration, and then, yeah, we need to return the value, not the node. Sorry about that. Okay, so that works. Let's run it on more examples. And now we can submit. Okay, so that passes. One thing though you can think of is, so the number of nodes in the tree in the range is 1 to 10 to the power of 5. So that's why we don't get ever none. But I wonder what happens if we get a BST with just maybe null values. So maybe something like just null. Okay, let's see. Okay, Okay, so Leetcode doesn't accept that as input, but if we want to make our code handle that, we can just refactor this portion here into a function and call that here. So what that would mean is something like next node. Okay, we'll pass the generator, and we can have this be done here. So this would be just return this, otherwise return none if we reach the end. And now we can just call this here. So here, since we passed the generator, we can just use that. And we do the same thing here so that we can avoid, if we get past an empty node, we can avoid problems. Yeah, let me use the examples. Okay, so this is just an indentation problem. And that passes test cases. One thing we can do is not none. This is the same thing as doing this, so we can remove that there. Yeah, so that's pretty much it. In terms of time complexity, here we are not using an extra space really, only we have this variable. And then this here is just one constant operation. Same thing here, we do only one next. Same thing here. Yeah, what's important is these two operations. And then in terms of the initialization as well, we do only one step, right? One step of the generation. So this is a good solution. Yeah, so this is the generator version. Now let's see how we can do the in-order traversal with iterative version. Yeah, so with that one, what I want to do first is just show you the implementation of in-order without any logic here, and from there we can, without this, just the vanilla in-order iterative traversal, and then from there we can adapt it to solve this problem. Okay, so I modified a little bit the examples they gave us so that we can run our code for the in-order traversal. So just to explain what it does, in-order traversal. So the code itself is going to be something like, we need to initialize our stack, and then we need to initialize a current node that points to where we are at, basically, each time. So this is our stack, and this is the current node. It points to the root initially. And then while there are elements in the stack, but this will fail in the initial iteration because the stack is empty. And so we want to also check, or we have a current pointing still to a node. So when the stack is empty, which means we popped everything out, and current is equal to none, which means where we are processing right now, we finished that off, right? So that will happen in this case when we do current dot left for 20. Which is none, and so we'll know we finished. Okay. And then here, what we need to do is go all the way to the far left, because remember, in-order traversal is left node and then right. And so what we need to do here is, while we have current, we want to go all the way to the left. And so we want to do current equal to current.left each time until we reach the last one. But to keep track of all the left elements that we go to, we need to add them to our stack here. So we add the element. And now once we processed all the left side, so in this case, let's do it for our example here. So let's have our stack. What this would mean in our test case here, we go current. So we start at the root here. Current is here. We go to the left. Okay, so current.left. And so first we add current, which is 5. So we add it. Okay, sorry. Let me just do this. Let me have spaces here for our tree. So this is our stack. yeah, to show that it's empty, actually, let's just, yeah, leave it like this. Okay, so we have 5, right? Now we go to the left at 3, and so we need to add 3 here. And then we go to the left again with this current left, and so we add 2. And then we go to the left again, we add 1. And then we try to go to the left again, but the left of 1 is none, and so we exit this while loop. So what should we do actually? This is the in-order traversal, so we should process 1 first, which means we need to pop this value. And so what we do here is current is equal to stack.pop. And so now our current value is equal to 1. And so we pop 1 out of the stack here. And now what should we do? Well, we should, if one had a right node, let's say maybe something here, X, we should process that first before moving up. We should process 1 first, which we did, but after that we should process right, because it's left node right for each subtree. And so what we need to do here is we need to assign to our current value. So here we say current, let me do this here, current equal to current.right. And here, whatever processing we want to do, we should do it here. Node current. Because we extracted 1, we need to process it before going right. Okay? So this is the code for the in-order traversal. And now let's just go and iterate through this list and see what we have. So let's say here if we are just adding it to a list, just so you can see that we get a final sorted list. So if we have that, we'll pop 1, and then we'll go to the right, but it's none. And so when we go again, we will find that current is empty, but we have elements in the stack, and so we will pop from the stack. And so we pop, and now what we should have here is 2. Okay, and so now we have 2, we need to process it, we add it to our list, we have 2. And then we do current equal to current right, and so 2 doesn't have a right, so it's also none. So when we go back up, current is none, and so we pop the stack again, which means here we pop our stack, and so here we have 3. Okay. And now we pop the stack, we process it, so we need to add 3 to our list. And then we do current equal to current.right. Now our current is pointing to 4. Okay, and so what do we do next? We go to the tree again. We go to the loop again. Current is not empty; it's equal to 4, and so we add 4 to the stack. So we add 4 here. Okay. Okay. Let's actually, since we popped from the stack, 4 would be here. And so we do current.left. The left of 4 is none, and so we find that this is none now. Current is none, so we go to stack pop. We pop 4. So here it was none, but we pop again, so it's 4, and so we add 4 to our list. And then what happens again? So once we have 4, we check if 4 has a right. It doesn't. It's none. And so when we go again to the loop, we pop again. So we pop it 4. We pop 5 this time. Okay. So we pop 5. We add it to the list. And we keep going. Basically, now we process right of 15, and then we go all the way to the left, so we are at 9. We add it to the stack, we pop 9, and then we process it, and we keep going until we reach 20. So, but this is the idea of the in-order traversal. So we have our stack and the current node. We keep traversing. We go all the way to the left, pop the node, process it, go to the right, and then go to the lefts of that right. So that's the main idea. Now let's see how we can apply it to our code here. Okay, so I added the stack. I added the implementation that we did for in order iterative traversal here. Now we just need to adapt it to support this. So the first step is initialization. We want to do that in the constructor. So this would be, since we will access these in next, we will do this here. Now in our next, you can think of the calls to next as while, and then for next we just need to do this logic here. We need to go all the way to the far left first, and so that would be self.current, self.stack. We just need to change the variables to point to this self version. And this here. So we go all the way to the left, and then for next, what do we need to return? Well, it's the processing step. And processing here for us in this case is just returning next. It's just returning the node, right? And so what we do is current is equal to this. So we'll make it a node actually, and this is the node that we need to return. This is the processing step. However, you can see here after the processing we need to move to the right node, right? Because we already returned this, so next time we want to return the right node if there is any. And so we want to, or at least to go to the right and then go all the way to the left and then go to the left of that node, right? So this is what we want to do here. So we need to do this assignment here. And now we just need to replace with self again. And when is the end? That's when the while loop ends, right? That means we are done. We processed all the nodes, and so here we need to return either stack or current still have elements. Either we still have elements to pop from the stack, and so here we'll do pop, or current still contains a node, so we need to process that node. And so we need to just do self.stack. So you can see how it maps very nicely to the in order traversal. This here we put it in next. This condition here is in has next because this determines whether we are done or not. And then the initialization needs to be in the unit function, right? And so just to iterate again, the logic is for next we go all the way to the left, okay, and then process the leftmost node. And then next time we get to the right? So we process the node, we need to go to its right, because it's a left node right, and then we keep doing that essentially. And yeah, this is pretty much it. So if we run this, okay, looks like we have one small thing here, and this is because it's not self.current right. What we are doing here is the elements we pop, that's what we get the right for. And so here this needs to be node.right. Okay? If I had said self.current here, I could say maybe if this is clearer, we could do node equal to self.current so that we can return that. And then do this, and that way we could do this. If this is closer to this and easier to understand, that works as well. Okay, yeah, sorry, this needs to be a copy, I think. Okay, yeah, let's just do the simpler version, which is this, and then we need to return the node, and then this needs to be node.right. We need to return the value, sorry. Okay. And if we submit this, that passes test cases as well. Yeah. Now let's go back to, I think it should work. Let's go back to what we were doing here, which is we said we want this, but we want node to be equal to, or maybe we could do val equal to self.current.val. So this is our processing step, and that way this here can be the same as this. Okay, let's try it again. Okay, this is here. This should be here. This should be val because we are no longer assigning a node. Sorry about these errors. Okay, so that should work now. Let's submit, and that passes test cases as well. Yeah, so I think in Order Traversal, it's good to be really familiar with both versions, the recursive version and the iterative version, just because some problems are easier to solve with an iterative version. Yeah, so that's pretty much it for this problem. Thanks for watching and see you on the next one. Bye.